Hello all, welcome to the second part of this tutorial in which we will be solving question on MLE and map estimate. In the previous part of this tutorial, we looked at the ordinary least square solutions derivation to obtain the optimal values of the parameter, and then we looked at the we took a two class problem, and then we obtained the base classifier for that specific problem. Okay, so without any further delay, let's delve into the current problem that we have. So in this problem, suppose x is uniformly distributed between 0 theta. Now that means that the x that we have is a uniform value between 0 theta, and then theta with theta greater than 0, and it is unknown. Okay, so then once we know the density of this case, now 1 over theta for x between 0 and theta and 0 otherwise. Okay, this is the density for x. Okay, so now suppose we have three IID samples. This is your data. Now the data that you have is x1 is 1.75, x2 is 0.5, x3 is 0.22. Okay, now what is the value of the likelihood function L theta given D? Now L theta, now with the given D as the data points. For theta is equal to 10, what will be the value? For theta is equal to 1.9, what will be the value? Okay, that is what we want to find. Now first we want to find the likelihood. Okay, so now value of the likelihood function okay, now L theta is equal to the whole data in which you have x1, x2, x3. Now since all of them are independent, now I can take the product of this. I is equal to 1 to 3, px of x equals to the value xi. Now please remember there is a lot of abuse of notations that are happening. Now this is nothing but the product of I is equal to 1 to 3, 1 over theta to the cube. There are three values. So and then indicator for 0 less than xi less than or equal to theta. Now what is this indicator random variable? See, indicator random variable is will take the value 1 when whatever function, if it is indicating that function, it will be 1, else it will be 0. Okay, so in this case, that this indicator random variable will take the value 1 if this xi is in between these two values. Okay, and this is a product of three indicator random variables. So now whenever a product of three indicator random variable will take 1 when all of them are in bound. Okay, so now let's write that the product of this indicator is 1 only when all samples lies in the range 0 comma theta. All the samples x1, x2, x3 lies in the range. Now that is what do you mean by that? 0 less than x1 less than or equal to theta. x2 is also in between 0 and theta. x3 is also in between 0 and theta. Now that means that theta is greater than or equal to max of x1, x2, x3. Okay. Now this makes total sense. Okay, if this has to satisfy, now the theta value should be the max greater than the maximum of this. Okay, now what does it mean? Now then the product of all these indicator random variable that we have for this is 1 when theta is greater than 2.2, 0 otherwise. Now that means that the value of the likelihood function will be 1 over theta to the power of 3 if theta is greater than 2.2, 0 otherwise. Okay, now this is the value for the likelihood function. Now he is asking that what will be the value at two given values of theta. It is very easy to look into. We already know now. Now L of theta equal to 10 will be 1 over 10 cube. L of theta equals to 1.9 is equal to 0. Why? Now one of the value is 2.2, so therefore this will be 0. Now this will have some meaning value. Okay. Till here it makes sense. Now consider the general case now where we represent three IID x1, x2, x3. Now plot the likelihood function. Now consider the case we have n IID samples, which is there. Okay. So now let's take the NIID sample case. I'll leave the plotting it to you. Okay. Very straightforward idea from now. Now in the general case of n samples, it's the same. Now L theta equals the product of all of them. So it will be I is equal to 1 to n 1 over theta to the power of n into the indicator is equal to xi theta. Now this is 1 over theta to the power of n into product of these indicator random variables. Okay. So now let's say that m that is there is equal to max of these x1, x2 so on till xn. Okay, it is the max of them. Now then the product of these indicators, now this will be 1 over theta to the power of n if theta is greater than m, and now xi also should be greater than or equal to 0, right? Okay, 0 otherwise. Now then now your L theta will be theta to the power of minus n, where theta is greater than m, and then xi is greater than or equal to 0 for all I, 0 otherwise. Now this will be the likelihood function. Okay. So now the next thing is, now once you have the likelihood for the n samples, now what is the MLE estimate of this theta? So now you have the likelihood, now maximum likelihood. Now what do you do? So now you want to get the MLE. Now to get the MLE, now MLE takes the maximizer theta should satisfy theta should be greater than m. And you should remember that this theta, now what are the values that it can take? It can take values from m to infinity. Okay. Now whenever theta is taking the value like this, our L theta will be theta to the power of minus n. Now, in this case, now it is evident to see that as theta increases, theta to the power of minus n decreases for all n greater than 0. N greater than 0 makes sense, but for the sake of completeness. Now this means that, see, what do you mean by maximum likelihood estimation? Now I have this likelihood. Now what theta now will give me the maximum value. Now as theta is increasing, my likelihood is decreasing. So now what is the maximum point that I can get? The maximum point that I can get is actually the leftmost now value, which is m. Correct? So logically it makes total sense. So the mean occurs. So the mean occurs only at the, oh sorry, not the mean, the max. Okay, the max value occurs only at the smallest allowed point. Now m is the smallest allowed point. Why? It is the maximum of all the x that you have. Okay, if the theta is taking any value less than m, so then the indicator will get 0. Now because of which your likelihood is not maximizing. Okay, now theta is equal to m, and then you have log of this theta is log of L theta, which is minus n log theta. Now you take the derivative of this with respect, partial derivative with respect to theta of minus n over by theta is less than 0 for all theta greater than 0. So it indicates, so L theta decreases, the log likelihood decreases with theta. Now, so the max value is at the left boundary, which is theta is equal to m. So which implies theta star MLE is equal to the max of x1, x2, so until xn. Now, and for our given data and for our given data, now theta MLE is 2.2. Okay, the maximum of those values. Okay, now this is just a small problem for you to say that now how do you calculate the likelihood and then obtain the maximum value, just to indicate that it is a very simple and a straightforward problem for us to work out. Okay, this is regarding MLE estimate. Now let's go to the map estimate. Now here now we want to estimate theta. Now what is the theta? Now theta is the probability of heads of a coin. Okay. Now the data contains n tosses in which n1 are head. Suppose we want a Bayesian estimate. Okay. Suppose the prior is 0.5 if theta takes the value 0.5, 0.5 if theta takes the value 0.6, 0 otherwise. Now this is your prior distribution. Okay. Now you have to take a conjugate prior. Now because of which your prior, which is that this is p theta and theta given d, Now both of them should be of the similar form. See, don't worry about this notations. I will be using the notations that are used in the class. Okay. So now how do we do it? Okay. So now we have to guess the estimate for theta and provide the estimation, then derive the map estimate. Now we'll be looking at obtaining the map estimate in this case. So now what is that we want to do? Now we want to estimate theta, which is probability of heads of a coin. Okay. We have n tosses, out of which we have nh tosses, which are heads, and then nt, which are tails, which is n minus nh. Okay. So now this is a binomial distribution. So I presume that all of you are clear with this, that this is a binomial distribution. Then PD equals to choose nh from n theta to the power of nh and 1 minus theta to the power of nt. Okay. Now this is our binomial distribution. Now we have prior is discrete. P theta is 0.5 when theta equals 0.5, 0.5 when theta is equal to 0.6. These are the two values, and for every other point it take 0 mass. Okay, and we all know that theta MLE in all these cases will be nh by n. Okay, so now guess the map. Now see, now you should remember in the Bayesian thing, P of P of theta given D is proportional to P of D given theta into P theta. This is your data. This is your prior and this is your conjugate prior. Both of them should have similar functional form. Now that means that similar functional form in the sense it can only take these two values. Okay, the probability in which it takes the value might change, but eventually it has to take only these two values. Okay, be very clear with that. You cannot take any other value apart from the 0.5 and 0.6. Now, as of now, you are giving for both of them equal probability. Okay, now your conjugate prior now can take now different values. Okay, so now let me guess for theta map. Now it is now theta map equal to 0.6 when nh by n is near h by n is greater than 0.5. Now theta map is 0.5 otherwise. This is what my guess is. Okay, now let's go ahead and look at this. Okay, so now this is my guess. No, it makes sense, no? If it is greater than 0.5, no, I'll take theta mat is equal to 0.6, which is the probability of head, which is there. I'll take 0.5 otherwise. Okay, fine. So now since I have P of theta is equal to 0.5 equals P of theta is equal to 0.6 is 0.5. Okay. Now what is that you want to compare? Okay. The comparison of P of theta given D is same as comparing P of D given theta. Correct? So now I can find the likelihood ratio. P of theta is equal to 0.6 given D divided by P of theta is equal to 0.5 given D is same as P of D given theta equals to 0.6. P of D given theta equals to 0.5 into P of theta equals to 0.6 into P of theta equals 0.5. Now these two values are same. You can cancel it out. Therefore, it becomes the ratio of this. Okay. So now this is P of D given theta equal to 0.6. The ratio becomes P of D given theta equals to 0.5. Now what do you mean by this? This is the ratio. When this value is greater than this, you choose 0.6. The other way, you choose the 0.5. Now choose theta equals to 0.6 if P of D given theta is equal to 0.6 is greater than P of D given theta equals to 0.5. Now, or you choose theta equals to 0.5 if P of D given theta is equal to 0.5 greater than D given theta is equal to 0.6. Okay. Now we want to compute these values now. Okay. These data conditioned on parameters. Now we have to compute these values. Okay. It's quite easy. Now we already know the functional form. We know this. These are binomials. We can compute them. So now P of D given theta is equal to 0.6. Now what is this? Choose NH out of n options. 0.6 to the power of NH, 0.4 to the power of NT. Now similarly, T given theta is equal to 0.5, it is choose NH out of n options, 0.5 to the power of n. See, now 0.5 to the power of NH, 0.5 to the power of NT will be there. Both n are there, so you can add. Now NH plus NT is n. So therefore it is like that. Okay. So now you want to find the ratio now. Now the ratio is D given theta is equal to 0.6 divided by D given theta is equal to 0.5. 0.6 to the power of NH, 0.4 to the power of NT divided by 0.5 to the power of n. See, what happens is this term is common. When you divide, this will get cancelled. So this is this term divided by this term. Okay. This I can rewrite it as 0.6 divided by 0.5 to the power of nh, 0.4 divided by 0.5 to the power of nt. This is 1.2 to the power of nh, 0.8 to the power of nt. Okay. Now, what is the thing that we are looking into? Now, we are saying that P of D given 0.6 is greater than P of D given theta equals 0.6. Theta equals 0.6, theta equal to 0.5. Now you can put them together. Now we have this ratio. So now this is same as 1.2 to the power of nh to the power of nh into 0.8 to the power of n minus nh is greater than 1. Okay. And then you can take the log on both sides. Okay. Now nh log of 1.2 plus n minus nh log of 0.8 is greater than 0. I have taken log on both sides. Okay. Now this is nh 1.2 minus nh ln of 0.8 plus n into ln of 0.8 now greater than 0. Now this is nh just a minute. Now what is just have what is this 1.2 divided by 2 divided by 0.8. That is 1.5. Okay. Now this is ln of 1.5 plus n into ln of 0.8 now greater than 0. Now this is nh is greater than minus n ln of 0.8 divided by ln of 1.5. Sorry. Okay. This I can rewrite as nh greater than n ln of 1.25 divided by ln of 1.5. Okay, just applying some logarithmic thing. Now 1 over ln of 1 over 0.8 will give you this value. Now this will be nh greater than 0.55 times n. Now this is the condition. Now finally what I want, I know only nh and then I know n. Now what is the estimate that I have to consider? Now when this is satisfied, now this is, I'm saying that I take the decision theta is equal to 0.6. When do I take this decision? When this condition is satisfied. Okay, now finally, now I will write that now when nh is approximately greater than 0.55 times n, then theta map, I will take it as 0.6. Otherwise, I will consider my theta map as 0.5. This is almost similar to what my assumption was, right? Not exactly, I did not get 0.55, but yeah, similar to our assumption that we made. Now, this is how you will be able to obtain from the given data the map estimate. Okay. So now here is where we stop. Now, a special thanks to Professor Shastri sir for curating these wonderful questions. Now, when with small questions, now can give us a lot more insights into the ideas. So we stop at this point. Now, I hope you enjoyed our overall discussion on obtaining base classifier MLE and map. We'll come up with other topics and then some other problems, exciting ones, in our coming tutorials. Meet you then. Bye bye.